Welcome to today's Explainer. We're kicking things off with a high-speed dive into the completely fascinating world of biomaterials. We're going to explore how brilliant scientists are taking everyday stuff we usually just throw in the trash and engineering it into some seriously cutting-edge solutions. We'll be breaking down whey protein isolate, hydrogels, big gels, tissue engineering, and even these super-powered oil adsorbents. It's an incredible journey from the waste bin straight to the high-tech laboratory, so let's just jump right in.
Okay, let's start with what sounds like a completely crazy question. Could the leftover dairy waste from your morning yogurt or, industrial cheese production actually be engineered to repair our skeletons? Whey protein isolate, or WPI, is this massive byproduct of the dairy industry, and for a really long time, it was basically just considered trash. But biochemists realized that this protein pack leftover has some unbelievable structural properties when you manipulate it just right. Or, hey, how about this one? Could ordinary, everyday potato starch be transformed into the ultimate environmental weapon to suck up massive oceanic oil spills? Well, researchers are finding that the answer to both of those questions is a resounding yes. But to really understand exactly how scientists are turning food byproducts into biological marvels, we kind of need to understand the fundamental architecture they're building. So the crucial starting point here is the hydrogel. You can think of a hydrogel as this microscopic 3D cage made out of natural biopolymers. And because these polymer chains are hydrophilic, meaning they just absolutely love water, they act like a molecular sponge. They can trap and hold huge amounts of water without dissolving. And that specific property makes them incredibly versatile for everything from delivering drugs inside the human body to actually engineering brand new tissues.
Now, obviously, scientists aren't just mixing these polymers in a beaker and guessing how they'll perform. They use advanced characterization techniques that basically give them superhero X-ray vision. Using nuclear magnetic resonance, or NMR relaxometry, they can track the exact molecular interactions. They're literally measuring how water moves inside the polymer. Meanwhile, scanning electron microscopy, or SEM, lets them visually zoom way in on the highly porous microarchitecture, while rigorous mechanical testing measures the sheer physical strength of the gels.
And when you actually use that scanning electron microscope, what you find is just wild. The microscopic architecture of these whey protein isolate gels reveals this highly interconnected, honeycomb-like porosity. And that's not just a random pretty pattern. That specific, porous microarchitecture is exactly what's needed to mimic human biology. It provides the perfect physical scaffold for human cells to latch onto, literally allowing for the growth of new bone and cartilage tissue directly inside the matrix.
But, for really heavy-duty jobs like bone and cartilage repair, a standard hydrogel is kind of flimsy. It's just not tough enough. So researchers level it up by creating hybrid nanocomposites. They mix oppositely charged natural polysaccharides like carrageenan from seaweed and chitin sawn from shellfish, and then they introduce an inorganic element, laponite nanoclay. Because the biopolymers weave themselves directly between the clay nanoplatelets, almost like mortar binding bricks together, they form this intensely strong, electrostatically cross-linked superstructure.
And this is where we see the true power of these nanocomposites. Because of that unique chemical structure, these biomaterials act like the ultimate super sponges for the human body. Get this, they boast jaw-dropping swelling ratios in the order of 6,000%. Just imagine a material capable of expanding to 60 times its original weight in fluid, all while completely maintaining its structural integrity. It is an absolute game changer for delivering nutrients, proteins, and drugs precisely where the body needs them.
All right, so let's shift gears for a second and look at how this builds into an entirely different field, dermatology and cosmetics. Here, we're looking at a battle between two competing physical forces. On one side, we've got our water-loving hydrophilic hydrogel, made from our whey protein isolate and sodium alginate. On the other side, we have a lipophilic oleogel, which is an oil-loving gel made from ethyl cellulose and sunflower oil. Naturally, oil and water hate each other, right? They always want to separate.
But what if you force them to get along? When you combine them using high-shear mixing, you get what scientists call a big gel. A big gel is basically a highly engineered molecular tug-of-war. It takes two completely immiscible, or unmixable, structured phases and locks them into one incredible, semi-solid material. By trapping both the water and oil phases together, you create a delivery vehicle that can handle both water-soluble and oil-soluble active ingredients at the exact same time.
The actual chemical engineering process to synthesize these things honestly looks a lot like a complex kitchen recipe. You've got your hydrogel components bubbling away at 80 degrees Celsius and your oleogel components melting together at 140 degrees.
You bring these two dramatically different mixtures together, homogenize them under intense physical shear, cast them into a mold, and then push them through one crucial final step.
That final step, freeze drying, is the ultimate secret to unlocking this material's potential. By freezing the biogel and placing it under a vacuum, scientists trigger a process called sublimation. This forces the frozen water inside to turn directly into a gas, cleverly bypassing the liquid phase entirely. It strips away the moisture while perfectly preserving that delicate structural framework, locking the biogel into a really light, airy, and incredibly stable matrix. And what you're left with is a material that has literal skincare superpowers, because the freeze drying leaves behind this perfectly porous matrix. We're talking porosities ranging from 35% all the way to 58%. It acts as a revolutionary transdermal delivery system. When you apply it to the skin, it slowly and consistently releases active ingredients while simultaneously hydrating the stratum corneum, which is the outermost layer of your skin. Plus, since they can tweak the exact ratio of hydrogel to oleogel, scientists can tailor the mechanical strength for pretty much any specific cosmetic need.
Okay, now let's take this brilliant bioengineering from the surface of our skin directly out into the deep ocean. We're shifting away from our dairy-based hydrogels to our next hero biomaterial, porous potato starch. But listen, this is definitely not the starch sitting in your kitchen pantry right now. Scientists have chemically modified it using a compound called methyl trichlorosilane, effectively rewiring its surface chemistry to tackle one of our biggest environmental threats.
By altering the surface of the starch at a microscopic level, researchers turned it into a super hydrophobic material. It develops this honeycomb, coral-like surface texture that creates microscopic pockets of trapped air. So when water hits it, the material treats the liquid like a literal trampoline. The water droplets simply bounce entirely off the surface without absorbing a single drop. It is completely, utterly waterproof. And we know it works perfectly because scientists measure what's called the water contact angle. If a drop of water sits flat and spreads out on a surface, the angle is low. But on this modified starch, the water beads up so tightly that the contact angle measures over 150 degrees, specifically around 151 degrees in their tests. In the materials science world, breaking that 150-degree barrier is the holy grail. It's the ultimate scientific benchmark proving extreme, super repellency.
So, why go through all the trouble of making potato starch waterproof? Well, here is the jaw-dropping payoff. Because the starch aggressively repels water, but absolutely loves organic compounds, it acts as a selective oil magnet. If you drop this biosponge into a simulated oceanic oil spill, it rapidly sucks up the heavy, toxic oil, pulling the contaminants deep into its microscopic pores, while completely ignoring the water around it. It basically cleans the water while remaining buoyant and perfectly intact.
So, we've seen how the whey protein left over from cheese can be engineered with incredible precision, monitored by advanced SEM and NMR, to build scaffolds that heal our bones, or big Ls that completely revolutionize cosmetic drug delivery. And we've seen how humble potato starch can be chemically weaponized to save our oceans from devastating oil spills, which leaves us with a fascinating final thought. If we can do all of this today with things we used to just throw in the garbage, what other everyday waste do you think scientists will engineer next to save our future?